Now, we have been talking about the different types of biomolecules and chemistry and how structure determines function. So we have to talk about how atoms, like atoms are anything that have protons, neutrons, and electrons in them. But based on how many protons they have, that's going to give them a certain structure. So they're going to have a certain function. So I talk about addresses. You can see my fireplace going in the back. Talk about addresses. So an atom simply has a proton, a neutron, and an electron. But if you have 7 protons, your address is 7 on the periodic table. That means you also have 7 neutrons, and we assume you have 7 electrons. So you're going to be nitrogen. And we talked about how elements come together to form compounds like water, sugars, proteins, things of that nature. And how, because of the electrons flying around on the outside and the fact that like charges repel, they have a hard time sticking to each other. So they have to use different types of bonds. And we went on to look at water, which is H2O, and the properties that water has, how it's cohesive and adhesive. Well, I want to take a second to talk about pH and acids and bases. You all know that water is H2O. Well, over time, water can disassemble. And so water, when it breaks down, will form what's called hydrogen ions and what are called hydroxide ions. Well, water, as it falls apart, should fall apart fairly equally. You should have equal numbers of hydroxide and hydrogen when water breaks down. And so, since these numbers are equal, water is neutral. The number of positives you get cancels out the numbers of negatives. Well, there's other molecules, other chemicals, that when you add them to water, they have a reaction. If you add something to water and it has a reaction, depending on how it breaks down, you're either going to be an acid or you're going to be a base. So for example, here again, water can break down into hydrogen ions and hydroxide ions. And in the case of water, when water breaks down, they're equal. So the positive hydrogen ions balance out the negative hydroxide ions. So water is neutral. However, other chemicals, if you mix them with water, depending on how that chemical falls apart, you'll determine whether it's an acid or a base. For example, hydrochloric acid. Well, the chemical formula for hydrochloric acid is HCl. So when you take hydrochloric acid and you mix it with water, the hydrochloric acid will fall apart into hydrogen ions and chloride ions. Well, the water already has hydrogen ions in it. So I'm going to add even more hydrogen ions to the water. Since I have increased the number of hydrogen ions, that means I have an acid. On the other end, something like sodium hydroxide, which is NaOH. When sodium hydroxide gets mixed with water, it breaks down into sodium and hydroxide. So when water breaks down, the amounts of hydrogen and the amounts of sodium are equal to each other. But when I add sodium hydroxide to the mix, I make even more hydroxide ions. So therefore, you're classified as a base. So again, just as a review, when water falls apart, it falls apart into hydrogen ions and hydroxide ions. And they should be equal to each other. They should cancel each other out because water is neutral. Well, if you add a chemical to water And when that chemical breaks apart, it adds more hydrogen ions, like hydrochloric acid, breaks down to hydrogen and chlorine. So I'm going to add even more hydrogen to the solution. I'm going to have something that's an acid. If I have a chemical that when it falls apart adds more hydroxide to the solution, like sodium hydroxide, that chemical is going to be a base. So if you end up with lots of hydrogen ions, that chemical is an acid. If you end up with lots of hydroxide ions, that chemical is a base. And pH basically measures how much hydrogen you have. I always say that pH stands for the power of hydrogen. Okay? So it's talking about those hydrogen ions. So low pH simply means you're getting closer and closer and closer to zero. You have a lower and lower and lower number. And a higher pH means you're getting further and further and further away from zero, so your numbers are getting bigger. So if you produce a lot of hydrogen, like the example I used here, so I take hydrochloric acid, and when it falls apart, it makes hydrogen and chlorine. And remember, let's pretend this is water. So there's already hydrogen there, so I made even more hydrogen. I've got myself an acid. And so pH measures how much hydrogen ions you have. And you guys know it ranges from 0 to 14. So right in the middle would be neutral. So basically water's neutral because when it breaks down, the hydrogen ions equal the hydroxide ions. If you have more hydroxide ions, you're going to be a base. And if you have more hydrogen ions, you're going to be an acid. So acids have a pH less than 7. Bases have a pH greater than 7. Well, in our bodies, we also have chemicals that work with acids and bases called buffers. And buffers are, since our bodies constantly make acids, and you guys know acids can burn things. Well, you don't want acids building up in our bodies because it can literally kill your cells. At the same time, bases can also burn. You've all had soap get in your eyes, okay? And you know it's not safe to drink bleach because they're bases, and bases can also kill our cells. Well, we constantly have acids and bases being made in our bodies. So we have to have something that takes care of them, that makes sure that we don't have these drastic pH changes so it hurts our cells. So we have chemicals called buffers, and buffers are chemicals that help kind of neutralize things. So anytime you mix an acid and a base together, you make something that's neutral. So an acid plus base, actually, you end up making salt and water. Well, you don't want to get rid of the acids in your body because some of the acids in your body you need. You don't want to get rid of all the bases in the body because some of the bases in your body you need. So we have a chemical that kind of cushions it. It kind of softens the blow. It kind of dilutes it, you can think of. And these chemicals are called buffers. Okay. So you guys know that acids have a pH range from 0 to 6.99. So 0 being really acidic, which means it has a lot of hydrogen ions in it. And this guy, you guys know, is almost neutral. So it might have 1 or 2 extra hydrogen ions in it. Acids all have a very sour taste to them, and you know that acids are liquids. So any type of fruit makes an acid, citric acid. Vinegar is an acid. If you're a base, you tend to go from 7.01 to 14. So up here, these are your stronger bases. They're going to have a lot of extra hydroxide in them. And bases taste bitter. Now, you know you're not supposed to put different bases in your mouth. You're not supposed to put soap in your mouth. You're not supposed to put bleach in your mouth. But you've all had soap get in your mouth before. And soap has a bitter taste to it. Coffee is a base. Coffee has an aftertaste. Well, the reason it's called an aftertaste is because the taste buds that let you taste bases are in the very, very, very back of your mouth. And you actually have to swallow to get the food that far back. So you actually taste the base after you swallowed. That's why it's called an aftertaste. but tastes all taste bitter. And bases have a very slippery feel to them. You know that shampoos are slippery. Cleaning products, Mr. Clean, Pine Sol, Lysol, Windex, Dawn dishwashing detergent, Tide liquid detergent. They all have that slimy feel to them. That's because they're all bases. And you know that pH paper can be used to indicate whether something is an acid or a base. Now it depends on what kind of pH paper it is as to what color it changes, but you've all used pH paper before in order to figure out what the pH is. Now, one more thing that we need to talk about. This just covered your notes on pH paper, or excuse me, on pH. I got to find it on my screen here, so excuse me for a second. It's going to get a little, I got to use this hand. Okay. I need you to find the PowerPoint or the page on your notes that talks about nucleic acids, because we need to talk about nucleic acids real fast. Okay. Nucleic acids are the last of the biomolecules. Okay. We've talked about sugars, and we've talked about how sugars are your carbohydrates and how they're made from just carbon, hydrogen, and oxygen. That's my big finger in the way. Okay. And we've talked about organic molecules having carbon and how we have these little building blocks called monomers. So these are my Legos. So one Lego is a monomer, just one. When I put them together to create my train, that's my polymer because I have lots of them. We talked about dehydration synthesis and how we make things. We talked about hydrolysis and how we break things apart. And then we had our 4 types of macromolecules. And we talked about how they're always in this order because of their complexity. So carbohydrates are first. They're made by plants. They're not that complex. So they don't have a lot of bonds. So it's like having a Ziploc baggie full of Legos. And you only have enough Legos to maybe make like a small chair or a small house. Nothing that's really complex. It didn't take you a long time to build something with those Legos. At the same time, it's not going to take a lot of time for you to pull them apart. And we talked about how Legos were your different types of sugars and starches. So we did all that. And then we talked about lipids and how lipids are your fats, oils, and waxes. They're also made from hydrogen and carbon and oxygen, but in a different structure. Remember, structure determines function. So carbs are more of a 1 to 2 to 1 ratio. Lipids don't have a lot of oxygen in them. And we talked about how nature wants you to eat lipids, so lipids taste good because lipids hold a lot of energy for us, and our brain is afraid of starving, so it actually wants you to store fat. So we talked about why that's so easy for you to gain weight, but it's hard for you to lose weight. Okay, and we talked about the different ways we use lipids in our body. We talked about the different types of fats in our body. And then we moved on to proteins. And notice proteins have an extra ingredient. They all have carbon, they all have hydrogen, they all have oxygen, but proteins have an extra ingredient, which is nitrogen. So if you have an extra ingredient, you're going to be even more important because you got more parts. And we talked about how proteins all form what looks like this beaded necklace, and each circle is an amino acid. So if you think of a pearl necklace, you have a bead, a string, a bead, a string. Well, the bead would be the amino acid, and the string is your peptide bonds. And we talked about structure determines function, and how I can take just one protein, and by changing its shape, I can make it do lots of different things. And we talked about different things in our bodies that we use proteins for. Now, the last thing we need to look at is on the back of your packet is these things called nucleic acids. And nucleic acids you know of as DNA and RNA. Now, we're going to spend a whole unit just talking about DNA and RNA and how they make proteins. But notice with nucleic acids, they are made of carbon, hydrogen, oxygen, nitrogen, and phosphorus. So carbs, lipids, proteins, and nucleic acids all have carbon, they all have hydrogen, They all have oxygen. Proteins have an extra ingredient, which is nitrogen. Nucleic acids also have nitrogen, but they have another ingredient, phosphorus. So if you just remember CHOMP, right? Not with an M, but with an N, you can remember the 5 elements that we use to make up our nucleic acids. And nucleic acids get their name because they're found in the nucleus. And these are your DNA and your RNA. And you guys all know this picture here. This is a picture of DNA. It's called a double helix. Well, DNA is what I call your cookbook because everybody knows what a cookbook is. Everybody's used a cookbook. Everybody's seen a cookbook. Cookbooks hold recipes in them. And recipes tell you how to make something. Well, that's what your DNA does for you. Your DNA is a cookbook. It has covers and it has pages on the middle. And the pages in the middle are your genes. So when we talk about cookbooks have recipes on them, and those recipes tell you how to make something, well, your DNA has genes, and your genes are your recipes. And those genes tell your body how to make something. Well, they tell your body how to make a protein. Well, we've been talking about Legos and how things come together to make these different structures. In the case of carbs, the Legos were monosaccharides. I start stacking a bunch of different Legos together, I make more complex sugars. In the case of your lipids, my monomers, my Legos, my blocks, were combinations of glycerols and fatty acids. In the case of proteins, my Legos, my beads, my building blocks, were amino acids. In the case of nucleotides, my Legos, in the case of nucleic acids, my Legos are these things called nucleotides. And nucleotides are always drawn as an L because they have 3 things in them. You're going to see when we talk about nucleic acids, you're going to remember the number 3. There's 3 letters in DNA. There's 3 parts to a nucleotide. There are 3 steps in making DNA. There's going to be 3 differences between DNA and its partner RNA. There are 3 steps in making RNA. There's 3 kinds of RNA, and then there's 3 steps in making a protein. Well, in the case of the nucleotide has 3 parts. It has a phosphate, and the phosphate's always at the top, and we'll talk about how this is actually running upside down. But if it forms an L, this part of your finger would be the phosphate. The crook part of your finger would be a sugar, and then your thumb is this thing called a nitrogen base. So all nucleotides have 3 parts: a phosphate, a sugar, and this thing called a nitrogen base. And depending on how they come together, we get our 2 types of nucleic acids. Okay. In the case of DNA, that's the one you're probably most familiar with. DNA stands for deoxyribonucleic acid. Okay. What that means, just so you'll know, it's in the nucleus. Okay. Anytime you see ribo means proteins. Well, we actually have a sugar called deoxyribose. You have a sugar called ribose, and you know it's a sugar because it's got OSC at the end. Deoxy simply means it's missing an oxygen. So deoxyribonucleic acid is what we call DNA. And DNA's job is to be your cookbook. It holds the instructions to make all the proteins you need. And your DNA has between 40,000 to 80,000 genes on it. There's an argument as to how many genes our DNA actually has. But that's like having a cookbook with 80,000 pages in it. 80,000 recipes. And you guys know, you've got cookbooks at home, your mom or your dad have cookbooks at home, and there's recipes in that cookbook that they've never, ever made. Well, the same is true with your DNA. There's recipes on there, we don't even know what they're for. But when we talk about genes, we're talking about recipes, and those recipes tell us how to make a protein. Well, DNA has a little partner called RNA, or ribonucleic acid, as you're going to see, functions in the making of proteins. You can just simply think of it as this. DNA is the entire cookbook, 80,000 pages. You just want to make brownies. You don't need every single recipe in that cookbook. You just want a brownie recipe. So you go to the cookbook and you find one brownie recipe. Or you go online and you find one brownie recipe. Well, you're going to see the problem is DNA's in your nucleus, We make proteins in a kitchen called the ribosome. And your DNA can't leave your nucleus. So somehow you've got to get the recipe from the nucleus to the kitchen, which is the ribosome. So it'd be like you going to the library and finding a recipe and taking a picture of it. And then you can take the picture back and use the picture that you took of the recipe to make the brownie. Or you can go online and you just download or print off just one recipe. That one recipe is going to be RNA. So at this point in time, your biomolecules packet should be totally finished.